Well, now we're moving along with our chapter on foundations of quantum theory and how it began. And the next chapter, or section 39.4 in our chapter on quantum theory, concerns a French physicist named de Broglie. And de Broglie had an interesting new hypothesis. And this really advanced our concept of what happens in quantum theory. Remember, first it was Planck who looked at cavity radiation and proposed that the energy of the oscillators in the walls had to be a multiple of Planck's constant times the frequency. This was Planck in 1900. Then Einstein in 1905 said, no, that's not the oscillators in the wall, it's the energy of the photon itself. And it is always a multiple of the frequency, and the momentum is always a constant divided by the wavelength. So Einstein did this in 1905. Then we had a confirmation of Einstein's work by Compton in 1923, and he confirmed that if you scatter an electron from a photon, the angle that they are scattered by confirms Einstein's particle hypothesis of the photon and not Maxwell's theory of the long electromagnetic wave. Well, now de Broglie was looking at all of this and he said, okay, what do we know? We know that we have two things: matter, that's regular matter, where the mass is greater than 0. And we have photons, or electromagnetic radiation. And it has a mass of equal to 0. Well, we know that for these photons, there are two equations that obtain, namely these two right here, that the energy is equal to a constant times the frequency, and momentum is equal to a constant divided by the wavelength. Well, you'll notice in these equations that de Broglie was studying, he said, well, frequency and wavelength are properties of electromagnetic radiation, but energy and momentum are properties of a particle, like this photon. So what we're really saying is, when we look at this whole theory, is that electromagnetic radiation is both a particle and it's an oscillation or a wave. Well, for ordinary matter now, we know we have energy and we know we have momentum. De Broglie made the stunning conjecture that if light or electromagnetic radiation, which has no mass, has both energy and momentum, particle-like attributes, and frequency and wavelength, which are wave-like characteristics, that maybe matter does too. So he made the conjecture that all matter had a wave associated with it, and the energy of a particle was given by Planck's constant times the frequency, and the momentum was Planck's constant divided by the wavelength. And this is what de Broglie did. He said the same thing that's true for electromagnetic radiation is also true for matter. Well, this was a stunning assumption. And of course, you can say, well, what does this mean? It means that if we had particles that had a certain energy and momentum, they're going to have a wave-like characteristic. What is the wave? We don't know. But he's just saying that they're going to have a wave-like characteristic. And this, of course, was like these other things, all of these were of the quality to win a Nobel Prize. So de Broglie won the Nobel Prize for this conjecture. Why? As simple a conjecture as it was, it turned out to be correct, as we will learn in the next section.